For 43 days, the world waited, and NASA stayed silent. Then, on November 19th, 2025, they finally spoke about the interstellar visitor known as 3I Atlas. Millions watched as officials Amit Kshatriya and Nicky delivered what they called the truth. But independent experts are calling it statistically impossible. The object passed closer to Mars than any comet in history. Amateur footage showed strange geometric structures. Yet, NASA released only blurry, low-resolution images, blaming sensor glitches and glare. They claimed it's a natural comet, but the data tables tell a different story. They didn't answer questions, didn't mention the mysterious ring, didn't reference the WOW signal coordinates. The official story doesn't add up. And tonight, we dive into what they didn't say, because the world may have just been lied to. Something strange happened on November 19th, 2025. And if you weren't paying attention, you missed the moment when trust in our space agencies might have fractured beyond repair. For 43 days, NASA went silent. Not the usual bureaucratic silence, where press releases slow to a trickle, but an active, deliberate absence of comment while the rest of the world watched something impossible unfold in real time. Amateur astronomers from Chile to Australia pointed their backyard telescopes at a visitor from beyond our solar system, an object designated 3I Atlas, and what they saw kept them awake at night, stacking images, enhancing frames, posting results that made professional scientists uncomfortable. They saw structures, geometries, patterns that comets simply don't make. The live streams multiplied across the internet like a fever. Someone in Portugal captured what looked like concentric rings around the object's core. A team in South Africa posted time-lapse sequences showing what they called a rotating lattice, faint but undeniable when you stacked enough exposures. In Japan, a retired optical engineer named Hiroshi Tanaka spent 72 hours straight processing frames from his 8-inch reflector and published an image that went viral within hours. It showed what appeared to be a double-sheath halo, two distinct shells of material surrounding the nucleus, maintaining their separation across multiple observation windows. These weren't blurry smudges. These were coherent, repeatable structures that appeared across different instruments, different atmospheric conditions, different processing methods. The amateur astronomy community was in chaos, split between those who insisted they were seeing signal and those who argued it had to be noise, but nobody could explain why the noise looked so organized. NASA said nothing. The European Space Agency issued a brief statement acknowledging observations were ongoing. The press waited. The world waited. And then, on November 19th at 3 p.m., Eastern Standard Time, NASA finally broke its silence. With a live stream from Goddard Space Flight Center. The announcement had come just 48 hours earlier, through a terse media advisory that promised, quote, release of images collected from various spacecraft and telescopes, end quote. Two officials appeared on screen. Amit Kshatriya, whose role in recent planetary missions had made him a recognizable face in space science communications, and Nicky, a scientist whose credentials were impeccable and whose presence suggested NASA was taking this seriously. Millions of people tuned in. The chat scrolled so fast it became unreadable. Everyone expected answers. What they got instead was a performance. That's how some independent analysts would later describe it. Not as a briefing, but as theater, carefully choreographed to deliver one central message. 3I Atlas is a natural, hypervolatile cometary body. The phrase appeared on the screen behind the speakers, rendered in NASA's trademark font against a backdrop of what they claimed were composite images of the object. The images were blurry. Frustratingly, maddeningly blurry for an agency that routinely produces photographs of Martian rocks sharp enough to count pebbles. The explanation came quickly, delivered with the practiced calm of officials who'd rehearsed their talking points. Sensor jitter, optical glare, the difficulties of imaging a fast-moving target at extreme range. They walked the audience through the dirty snowball model, the classic comet structure of water ice and dust, outgassing as it approached the sun, jets of vapor creating asymmetric thrust that altered its trajectory in perfectly natural ways. But here's what they didn't mention. Not once in 45 minutes did anyone address the ring structures that amateur observers had been documenting for weeks. Not once did they acknowledge the geometric patterns, the coherent shapes, the anomalies that had sparked so much debate. When questions came from the curated press pool, they were softballs about mission timelines and future observation windows. No independent journalists were called on. Nobody asked about the trajectory coordinates, which multiple analysts had noted aligned, with unsettling precision, toward the same region of sky where the famous WOW signal was detected back in 1977. Nobody mentioned that detail because NASA's presentation had already moved on, pivoting to discussions of volatility rates and sublimation models, drowning any controversy in technical language that sounded authoritative but left critical questions unanswered. Independent experts started raising alarms before the livestream even ended. A dynamicist from Berkeley posted on social media that the outgassing rates NASA cited were, quote, statistically impossible given the observed acceleration parameters, end quote. A spectroscopist in Germany noted that the vapor production estimates contradicted the brightness measurements by at least an order of magnitude. An imaging engineer with 20 years of experience working on planetary missions stated flatly that sensor jitter doesn't produce the kind of coherent noise patterns visible in NASA's own released frames. These weren't conspiracy theorists shouting into the void. These were serious researchers, many with NASA collaborations on their CVs, raising technical objections that demanded technical responses. And NASA simply absorbed the criticism without acknowledgement, as if the briefing had closed a chapter rather than opened one. The more you looked at the presentation, the stranger it became. Data tables appeared on screen for seconds at a time, too brief to screenshot clearly. Footnotes in tiny font that mentioned exposure times and processing algorithms without elaboration. One analyst who managed to freeze frame the metadata noted something odd. The timestamps on supposedly sequential images didn't cluster the way you'd expect for a continuous observation campaign. Some showed gaps of hours, others seemed bunched within minutes, creating a patchwork timeline that suggested selective release rather than comprehensive documentation. It felt less like transparency and more like curation, choosing which pieces of the puzzle to show while keeping others locked away. So here's where we are. NASA has given us their official story. 3I Atlas is a comet, unusual perhaps in its trajectory and composition, but fundamentally natural and explicable within known physics. And yet the evidence they presented seems weaker than what amateur astronomers are collecting in their backyards. Either we're witnessing catastrophic incompetence in science communication from an agency that's had decades to perfect the art, or we're watching something more deliberate unfold. A narrative being constructed not to inform, but to manage. And that possibility, more than any speculation about alien probes or artificial structures, should keep us up at night. Because if NASA isn't telling us the whole truth about 3I Atlas, we need to ask ourselves, what could possibly be important enough to justify the lie? The amateur astronomy community operates in a strange space between professional science and citizen investigation, equipped with technology that would have seemed like magic 30 years ago, but still considered outsiders by institutional gatekeepers. When 3I Atlas first appeared in tracking systems, these observers mobilized with remarkable speed. Within days, networks spanning continents had coordinated observation schedules, sharing data protocols and processing techniques refined over years of comet hunting and asteroid tracking. What they captured wasn't just interesting, it was profoundly weird. Consider the imaging process for a moment, because understanding how these pictures get made matters when evaluating their credibility. Amateur astronomers don't just point and click. They capture dozens or hundreds of exposures of the same target, then use specialized software to align those frames with subpixel precision, accounting for atmospheric distortion, telescope tracking errors, and the target's own motion against the background stars. This stacking technique, the same basic method professionals use, dramatically increases signal-to-noise ratio, revealing details invisible in any single frame. When properly executed, it's devastatingly effective. And what it revealed about 3I Atlas didn't match NASA's blurry, jittery images at all. The ring structures appeared first in data from Southern Hemisphere observers who caught the object during favorable viewing geometry. Multiple independent teams, using different telescopes and processing software, reported the same feature: a toroidal shape, like a donut of material surrounding the nucleus. The geometry was too regular to dismiss as random dust distribution. One Chilean team published a sequence showing the ring maintaining its structure across 3 nights of observation, rotating but not dispersing, which shouldn't happen if it were just loose particles in orbit. Dust spreads. Dust diffuses. This didn't. Some frames showed what looked like shadows rotating across the ring's surface, suggesting either local density variations or possibly even 3-dimensional structure. One particularly striking image, captured by an amateur in New Zealand using stacked exposures totaling 4 hours of integration time, showed what appeared to be a double ring system, 2 concentric structures with a clear gap between them, both centered on the same nucleus. Then there was the Mars flyby, which should have been the definitive moment for high-resolution imaging. On October 2nd, 2025, NASA's Mars Reconnaissance Orbiter, equipped with the HiRISE camera, the most powerful telescope ever sent to another world, captured 3I Atlas passing at approximately 18.6 million miles from the spacecraft. For context, that's closer than any interstellar object has ever been photographed by humanity's space-based assets. HiRISE can resolve features on Mars the size of a coffee table from orbit. It should have given us extraordinary images of 3I Atlas. What NASA released instead were frames described charitably as soft, lacking the dramatic detail that ground-based amateurs were somehow achieving, despite looking through Earth's atmosphere. The disparity was jarring enough that even cautious scientists started asking questions. The orbital dynamics added another layer of strangeness. 3I Atlas was moving fast, really fast, clocked by stereo spacecraft observations at roughly 209,000 kilometers per hour as it tore through the inner solar system. That velocity was consistent with an interstellar origin, an object falling into our sun's gravity well from the depths of space. But its trajectory showed peculiarities. Small deviations from the path that pure gravity would predict, accelerations that NASA attributed to outgassing, the rocket effect from vaporizing ice. Comets do this all the time. Except independent dynamicists ran the numbers and found something troubling. The magnitude and direction of these non-gravitational accelerations didn't quite fit the standard models. Getting them to work required assuming outgassing patterns that seemed contrived, jets firing in precisely the directions needed to explain the observed motion. Without clear evidence, those jets existed in the expected locations. NASA's explanation for the image quality issues centered on sensor jitter and glare. Sensor jitter is real. Spacecraft experience tiny vibrations. Attitude control thrusters fire. Thermal expansion and contraction cause subtle movements, all of which can blur images if exposure times are long enough. Glare is also real. Bright sources can scatter light within optical systems, creating halos and artifacts. Both explanations sound reasonable until you start examining what sensor jitter actually looks like in spacecraft imagery. It produces random smearing, different in each frame, averaging out when you stack multiple exposures. What some analysts claim to see in the released NASA frames wasn't random. The blur patterns looked consistent, almost systematic, as if something in the processing pipeline was uniformly softening the data. One imaging engineer pointed out that modern image processing includes sharpening algorithms as standard practice. NASA could have sharpened these images. They chose not to. Why? Compare that to the amateur data. Yes, Earth's atmosphere introduces its own distortions, but adaptive processing techniques can compensate remarkably well, especially when you're stacking many exposures taken under varying atmospheric conditions. The turbulence averages out differently in each frame, while the real target signal remains consistent, allowing software to distinguish true structure from atmospheric noise. The result is that patient amateurs with mid-sized telescopes were producing images showing more apparent detail than NASA's spacecraft. That shouldn't be possible unless NASA was deliberately choosing to release lower quality versions of their data. Some observers noticed another oddity in the released materials. The images NASA showed came from multiple instruments. HiRISE on Mars Reconnaissance Orbiter, cameras on stereo spacecraft, ground-based facilities they coordinated with. But the level of detail varied wildly between sources in ways that didn't correlate obviously with the expected capabilities of each instrument. Some frames from theoretically superior systems looked worse than those from less capable ones. It suggested selective processing, or perhaps selective release, showing frames that supported the Comet narrative while withholding ones that might raise uncomfortable questions. The momentum transfer problem bothered physicists specifically. When a comet outgasses, the expanding vapor carries momentum, pushing the nucleus in the opposite direction through Newton's third law. Calculating this requires knowing how much gas is being produced and in which directions. NASA's briefing implied they'd done these calculations and found everything consistent with natural comet behavior. But when independent researchers tried to reproduce the analysis using the parameters NASA had published, they couldn't make the numbers work without invoking implausibly high outgassing rates or very specific jet geometries that seemed suspiciously convenient. One dynamicist described it as, quote, fitting a hypothesis to the data rather than testing whether the data supports the hypothesis, end quote. So we're left with a puzzle. If NASA's imaging is limited by legitimate technical constraints, why are amateurs getting better results? If their Comet model is robust, why can't independent scientists reproduce their momentum calculations? If 3i Atlas is just an unusual but natural object, why does explaining its behavior require threading needles through parameter space that should have comfortable margins? Maybe the agency is right, and everyone else is overthinking ambiguous data. Or maybe, just maybe, the evidence NASA chose not to show is more important than the evidence they did. And that question won't go away just because they held a briefing and declared the case closed. Professional scientists have a saying, the devil is in the metadata. Raw images and pretty visualizations tell one story, but the technical specifications, the exposure parameters, the calibration notes, the processing logs, these tell another. When NASA released their briefing materials, they included supplementary files, PDFs with data tables, image specifications, observation logs. Most people ignored them. A few people didn't. What they found buried in footnotes and technical appendices was, in some ways, more revealing than anything shown during the live stream. Start with the basics. Astronomical observations include timestamps, precise records of when each exposure was captured, necessary for coordinating observations and understanding the viewing geometry. The release data tables for 3i Atlas showed something odd. Timestamps clustered in ways that didn't match a systematic observation campaign. You'd expect either regular intervals if they were monitoring continuously, or random scatter if they were opportunistically grabbing images when other priorities allowed. Instead, the pattern looked selective. Dense clusters of observations during some periods, conspicuous gaps during others. One researcher mapping the timeline noticed that some gaps corresponded to periods when amateur observers were reporting the most dramatic structures. Correlation isn't causation, but the pattern was curious enough to note. Exposure durations varied strangely too. Standard practice when imaging faint moving objects is to optimize exposure time for a balance between collecting enough light and not blurring the targets. Motion. Too short and you get noise, too long and you get trailing. NASA's images used wildly different exposures for supposedly similar observation geometries. Some very brief, others surprisingly long. A few imaging experts suggested this might indicate they were experimenting with technique, which would be odd for such a high-priority target, or that different frames were intended for different purposes, which raises the question of what purposes NASA had in mind. Then, there's the velocity residuals, a technical term for discrepancies between predicted and observed motion. When tracking objects in space, astronomers create mathematical models predicting trajectories based on gravitational forces from the sun, planets, and other bodies. Real objects never follow these predictions perfectly. Comets have outgassing. Asteroids have irregular shapes affecting how they tumble. Measurement errors accumulate. The art is distinguishing meaningful deviations from noise. NASA's published orbit solution for 3i Atlas included correction terms, small accelerations attributed to non-gravitational forces, the comet outgassing they emphasized in the briefing. But when independent dynamicists examined these terms closely, Some argued they were larger than expected and pointed in directions that seemed to require very specific assumptions about where and how the outgassing occurred. One particularly thorough analysis, circulated privately among planetary scientists, attempted to model the outgassing needed to produce NASA's reported velocity residuals. The author concluded that explaining the observed non-gravitational accelerations required either implausibly high volatility, meaning the comet was producing vapor at rates that should have made it much brighter than observed, or jet activity that was precisely oriented to produce the accelerations while somehow not leaving obvious evidence in the imagery. Both scenarios seemed contrived. The simplest explanation, the author noted carefully, was that the orbit solution was preliminary and further refinement would resolve the inconsistencies. But NASA had presented it as definitive. They'd closed the investigation before the numbers fully worked. Radio observations added another piece to the puzzle. On October 24, 2025, the Meerkat Radio Telescope Array in South Africa detected hydroxyl absorption lines at 1.665 and 1.667 gigahertz, signatures consistent with water vapor breaking apart in sunlight. This was significant because hydroxyl, OH, is a tracer for cometary activity. Finding it supported NASA's narrative, except the details were more complicated than the briefing suggested. Meerkat had attempted observations earlier, on September 20th and 28th, and detected nothing. The October 24th detection occurred during solar conjunction, a geometric alignment where Earth, the Sun, and 3i Atlas roughly lined up, allowing the radio telescope to detect absorption of solar radio emission passing through the comet's atmosphere. It was legitimate science. But the fact that earlier attempts found nothing raised questions about how active this supposedly hypervolatile comet actually was. Absorption versus emission matters here. Meerkat detected absorption, radio waves from the Sun being partially blocked by hydroxyl molecules in the comet's vicinity. Earlier attempts were looking for emission, hydroxyl molecules naturally radiating at these frequencies. Not finding emission doesn't necessarily mean hydroxyl isn't there, just that it wasn't abundant or excited enough to emit detectably. But the timing bothered some researchers. Why did the comet suddenly become active enough to show strong absorption features right when the geometry was favorable for detection, after being quiet during earlier observations? Maybe it crossed some threshold distance from the Sun and volatility ramped up suddenly. Or maybe something else was going on. What NASA chose to emphasize versus what they buried in footnotes created a pattern. The briefing highlighted data supporting the comet model: volatility, outgassing, jets, all cometary behaviors. Data that complicated the narrative, the velocity residuals that didn't quite fit, the early radio non-detections, the image quality issues that seemed worse than they should be. These details appeared only in technical appendices written in jargon that most journalists and public observers wouldn't parse carefully. It's a classic communication strategy. Tell a simple story prominently. Hide the complexity where only experts will look. Bet that most people won't dig deeper. It works usually. But this time enough people were paying attention that the strategy backfired, creating more suspicion than transparency. Some analysts started calling it the controlled narrative hypothesis. The idea wasn't necessarily that NASA was lying outright, but that they were managing information flow, releasing data in ways designed to support a preferred interpretation, while making alternative explanations harder to pursue. This could be motivated by legitimate concerns, avoiding public panic if the object's nature was truly ambiguous, maintaining institutional credibility in the face of wild speculation, keeping scientific discourse from being overwhelmed by fringe theories. Or it could be something else. Maybe NASA itself was uncertain and chose to project confidence rather than admit ambiguity. Maybe internal disagreements about interpretation led to a political decision to present the least controversial conclusion. Maybe they genuinely believed their comet model, but recognized that releasing all their data would fuel endless debate, so they curated the release for clarity. Whatever the motivation, the effect was corrosive. Trust erodes not just through lies, but through selective truth-telling. When people notice that important details only emerge through careful reading of footnotes, they start assuming the main narrative is incomplete or misleading. NASA's briefing was supposed to settle questions. Instead, it multiplied them, because the data they released, when examined closely, supported the comet hypothesis, only if you didn't look too hard. And once you started looking, you found cracks. Small cracks, maybe, but cracks in a story that was supposed to be definitive. And through those cracks, other possibilities started emerging, possibilities that NASA very clearly did not want anyone discussing in public. Which makes you wonder what they saw in the data they didn't release. Science operates on reputation and peer review, a system built on public disclosure and reproducible results. When you want to criticize an established narrative, you publish your analysis, put your name on it, let other experts evaluate your claims. That's how it's supposed to work. But sometimes the system fails, not because the science is wrong, but because the political and institutional pressures become so intense that honest dissent becomes professionally dangerous. That's what happened in the weeks following NASA's 3I Atlas briefing. Scientists with serious concerns started organizing, but not publicly. Not yet. The networks formed quietly at first, private Slack channels with invitation-only access, encrypted email threads that circulated draft papers never submitted for formal review, Zoom calls where participants were careful not to record. These weren't fringe figures prone to conspiracy thinking. These were mid-career researchers with publications in major journals, senior scientists who'd built careers on rigorous analysis, early career postdocs who understood that speaking up could end their prospects for faculty positions. They shared a common frustration. NASA's narrative didn't survive careful scrutiny, but saying so publicly risked being lumped in with alien conspiracy theorists, or worse, being quietly blacklisted from future observing time allocations, or grant funding. So they talked in private and started building cases they hoped would eventually become undeniable. Spectroscopists focused on the photochemistry, the processes that break molecules apart in sunlight. NASA's model assumed water ice sublimating from the surface, those water molecules then getting hit by ultraviolet light and splitting into hydrogen and hydroxyl. The hydroxyl was what Meerkat detected. Simple enough. Except the rates didn't work. Several researchers independently calculated how much water vapor would need to be present to produce the observed hydroxyl absorption, then worked backward to figure out how much outgassing that required. The numbers were uncomfortably high. To maintain those hydroxyl densities, 3I Atlas should have been producing vapor at rates that would make it significantly brighter in visible light, with a much more dramatic cometary tail. The actual brightness was modest. One spectroscopist put it bluntly in an off-the-record conversation. Either our understanding of cometary photochemistry is fundamentally broken, which would be surprising after decades of studying comets, or the hydroxyl detection doesn't mean what NASA claims it means. The dynamicists had different concerns, but reached similar conclusions. They focused on momentum transfer, the physics of how outgassing creates force. When vapor escapes a comet's surface, it carries momentum, and conservation of momentum means the comet gets pushed in the opposite direction. Calculate this correctly, and you can predict how the comet's orbit will deviate from pure gravitational motion. NASA claimed their observations matched these predictions, but several independent teams tried to reproduce the calculations using the parameters NASA had published and couldn't get agreement. The accelerations observed were too large, or pointed in the wrong directions, or required outgassing geometries that seemed implausibly specific. One researcher described it as, quote, having to tune 4 or 5 free parameters to exact values with no independent constraints, which is a fancy way of saying the model was overfitted, forced to match observations rather than genuinely explaining them. Getting the momentum conservation to work required mass loss rates that created other problems. Comets are finite objects. They have finite reservoirs of volatile material. Sustained outgassing at the rates needed to explain 3I Atlas's orbital deviations should deplete those reservoirs relatively quickly, especially for what NASA described as a hypervolatile body. Yet the object maintained activity across weeks of observation with no obvious decline. Either it was much larger than the images suggested, hiding vast reserves of ice beneath a thin surface layer, or the outgassing wasn't as symmetric or simple as NASA's model assumed. Both possibilities opened uncomfortable questions. A larger nucleus would create different observational signatures. More complex outgassing would require more complex explanations, undermining the simple dirty snowball narrative. Imaging experts contributed a different type of critique, focusing on the signal processing and noise characteristics. These were people who built cameras for spacecraft, who understood intimately how sensors behave, how images get corrupted by various error sources, how processing algorithms can enhance or suppress different features. Several noted that the coherent patterns some amateur observers were finding shouldn't survive noise reduction if they were truly artifacts. Real sensor jitter creates random blur that averages differently in each frame. Real glare creates specific optical artifacts that look nothing like geometric rings. When multiple independent observers using different instruments all report similar structures, dismissing them as noise becomes harder to justify. One imaging engineer stated flatly that if NASA wanted to prove the structures were artifacts, they should release the raw, unprocessed frames and let independent teams analyze them with full access to calibration data. That hadn't happened. Instead, NASA released pre-processed images with embedded corrections that made forensic analysis nearly impossible. The conversation in these private channels oscillated between technical critique and broader speculation about why NASA was handling the situation this way. Three hypotheses emerged repeatedly. First, the management of fear hypothesis. Maybe the agency genuinely didn't know what 3i Atlas was, found the ambiguity concerning, and chose to present a simple natural explanation rather than admit uncertainty and fuel public anxiety. Historical precedent existed for this. During Cold War decades, official explanations for atmospheric phenomena sometimes obscured genuine confusion about what military or civilian observers were seeing. The modern version would be scientists recognizing that saying, "we're not sure," would unleash media chaos, so they defaulted to the most conventional interpretation they could defend. Second, the retrofitting hypothesis. NASA got caught off guard by how weird 3i Atlas turned out to be, initially assumed it was just an unusual comet, then found evidence complicating that picture, but had already committed to the comet narrative publicly. Rather than walk back their initial framing and admit they'd spoken prematurely, they doubled down, massaging the data presentation to fit the story they'd already started telling. This would be institutional inertia plus face-saving, not malicious, but not exactly transparent either. Anyone who's worked in large organizations recognizes this pattern. The first explanation becomes politically entrenched, and contradicting it requires political capital nobody wants to spend. Third, the correct but constrained hypothesis. NASA's Comet model was actually right, or close enough, but institutional pressures shaped how they communicated it. Political leadership wanted no controversy. Public affairs offices worried about feeding internet conspiracy theories. Budget battles made appearing uncertain dangerous when asking Congress for funding. So even though scientists internally might have been debating details and refining models, the public message got simplified, polished, made definitive, even when the science was still iterating. The result was accurate in broad strokes, but misleading in the certainty it projected, creating an opening for critics to question whether the whole story was being told. These private discussions included something else that rarely appeared in public scientific discourse: genuine uncertainty and humility. Scientists admitting they didn't have all the answers, that the data was messier than they'd like, that conventional explanations had gaps they couldn't yet fill. This kind of honest complexity doesn't translate well to press releases or live-streamed briefings, which demand clear narratives and confident conclusions. But it's the actual texture of frontier science, where most questions don't have neat answers, and progress happens through incremental refinement of partial understanding. NASA's briefing erased all that complexity, presenting a finished story where the real work was still ongoing. And that erasure, perhaps more than any specific scientific dispute, was what bothered the off-the-record rebels most. Science is supposed to be about following evidence wherever it leads, admitting ignorance when appropriate, prioritizing truth over convenience. Instead, they were watching institutional imperatives override scientific values, and that felt like a betrayal worth resisting, even if they had to do it in the shadows for now. Mainstream science operates within boundaries, not because scientists lack imagination, but because extraordinary claims genuinely do require extraordinary evidence. The history of astronomy is littered with exciting anomalies that turned out to be instrumental artifacts, misinterpreted data, or natural phenomena that seemed weird until better measurements clarified them. Professional skepticism serves science well, but that skepticism has limits. At some point, when enough anomalies accumulate and conventional explanations require too much special pleading, the boundaries start to feel less like prudence and more like dogma. In the case of 3I Atlas, that point arrived for some researchers when they started seriously modeling alternatives to the Comet hypothesis. What they found was unsettling, not because these alternatives were proven, but because they seemed to work better than they should. The ring structures remained the most visually striking anomaly, the feature that grabbed attention even from casual observers. Multiple independent imaging teams reported toroidal geometries, donut-shaped distributions of material that maintained coherence across observation windows. Conventional dust dynamics doesn't easily produce this. Dust around comets typically forms diffuse clouds, shells expanding outward, sometimes jet structures shooting in specific directions. Stable rings require something holding them in place, some organizing principle beyond simple gravitational orbits. Several physicists started exploring whether plasma effects could create such structures. Charged particles can be trapped in magnetic fields, forming toroids around magnetized bodies. But comets aren't supposed to have significant magnetic fields. Their nuclei are essentially piles of ice and rock, not rotating metallic cores generating dynamos, unless the nucleus was something else, unless it had interior structure that wasn't icy at all. One theoretical paper that circulated privately modeled a plasma torus scenario. If 3I Atlas had even a modest magnetic field, something on the order of a few hundred nanotesla, and if it was outgassing ionized particles rather than just neutral water vapor, those charged particles could be magnetically confined into stable ring geometries. The model worked mathematically. It predicted ring sizes and densities roughly matching observations. But it required assumptions that seemed absurd for a natural comet. An internal magnetic field source, significant ionization of outgassing material, and stability that should persist across varying solar wind conditions. The author included a section honestly acknowledging these difficulties, then noted that if you were designing a spacecraft to travel through interstellar space and wanted passive radiation shielding, a magnetic bottle containing ionized material would be a remarkably efficient solution. The paper never used the word artificial, but the implication hung over every equation. Then someone noticed the wow signal coordinates. This detail appeared first in obscure forum threads, was dismissed as numerology, then resurfaced when multiple people independently confirmed the alignment. On August 15th, 1977, the Big Ear radio telescope in Ohio detected a 72-second radio signal from space. Strong and narrowband, exactly the kind of signal SETI researchers had been hoping to find. It was never detected again, despite decades of follow-up searches. The signal came from a direction in the constellation Sagittarius. Right ascension, 19 hours 25 minutes. Declination, negative 27 degrees. When researchers plotted 3I Atlas's inbound trajectory, its path across the celestial sphere, they found something strange. The object's apparent origin point, if you traced its hyperbolic orbit backward through space, passed within a few degrees of the WOW signal coordinates. Not exact, but close enough to notice. Close enough to make you uncomfortable. Statistical arguments erupted immediately. How many points are there on the celestial sphere? Tens of thousands of square degrees. How many interstellar objects have we detected? A handful. What are the odds one of them would randomly pass near one famous coordinate from SETI history? The math depends on how generous you are with definitions of near and how you account for selection bias. Skeptics argued that with enough famous sky coordinates and enough objects, coincidences happen. Believers countered that the WOW signal was unique, not just another random point, and that 3I Atlas was unique among interstellar objects in its behavior. The argument couldn't be resolved with statistics alone. But it added another element to an already strange picture: an object behaving weirdly, showing possible geometric structures, arriving from approximately the direction of the only radio signal in history that everyone agrees looked artificial. Maybe it meant nothing. Or maybe someone out there sent a probe along the same vector as their earlier signal, and we were too invested in conventional narratives to recognize it. The three-shell model emerged from attempts to explain all the observational data simultaneously. Start with the fact that 3i Atlas showed evidence of volatility, but also structural coherence. Outgassing suggests a loose, icy body. Geometric structures suggest something more organized. What if both were true? One proposed architecture involved three distinct layers: an inner core, possibly solid or at least densely packed, serving as the structural foundation; a middle shell of dust or plasma, magnetically confined or mechanically supported, creating the ring-like features; and an outer envelope of volatile material, producing the observed outgassing and comet-like appearance. This wasn't one object but a nested system, each layer serving different functions. The inner core could be inert, maybe even metallic. The middle shell could be active, responsive, possibly even controllable. The outer shell could be camouflage, deliberate or incidental, making the whole thing look cometary to casual observation. Models like this weren't pulled from thin air. Engineers thinking about interstellar mission design had proposed similar architectures for radiation shielding, thermal management, and course correction. A solid inner core provides structural integrity against the stresses of high-velocity travel through the interstellar medium, where even sparse gas becomes erosive at relativistic speeds. A plasma or dust shell, properly confined, shields against cosmic rays and charged particles. An outer ice layer provides reaction mass for maneuvering via sublimation jets, exactly the kind of propulsion NASA claimed explained 3i Atlas's trajectory deviations. The difference was intent. Designed versus accidental. Controlled versus random. If you looked at 3i Atlas through the lens of mission engineering rather than natural astronomy, its features started making different kinds of sense. Which led to the most speculative question of all. If it was engineered, what was its mission? Four possibilities circulated in the more theoretical discussions. First, a deliberate reconnaissance probe, sent by whoever to observe this solar system, its trajectory designed to pass through the inner system for close observation of the planets, then continue outward carrying data home. Second, an autonomous scout, part of a network of such probes scattered across the galaxy, each following pre-programmed paths, collecting information, possibly waiting for instructions. Third, a data courier carrying information encoded in its structure or materials, meant to be intercepted and decoded by anyone technologically capable, a message in a bottle thrown across interstellar space. Fourth, a derelict, a mission that ended long ago, its systems failed or depleted, drifting now as space junk from some civilization's ancient exploration program, still bearing traces of its original purpose, but no longer functional. Each scenario had different implications for how we should respond. A reconnaissance probe might be gathering data. Right now, observing our attempts to observe it, learning about our technological capabilities. An autonomous scout might not even register our presence, operating on timescales and with priorities completely alien to human thinking. A data courier was potentially the most exciting, suggesting someone wanted to be found, wanted to communicate, encoded something worth discovering. A derelict was perhaps the most melancholy, evidence that other civilizations tried and possibly failed, or succeeded once then disappeared, leaving only artifacts drifting through the void. But here's the critical point. None of these hypotheses were proven, not even close. Every single one remained wildly speculative, supported only by ambiguous data that could be interpreted multiple ways. Mainstream science rightly demanded better evidence before taking such ideas seriously. The problem was that NASA's handling of the situation made getting better evidence harder. By declaring the case closed, by presenting a comet narrative with more certainty than the data justified, by not releasing raw data for independent analysis, they'd created an environment where speculation flourished because rigorous investigation was being blocked. If NASA wanted to kill the artificial hypothesis, the best approach would be radical transparency. Release everything. Invite independent analysis. Let the scientific community examine the data thoroughly and reach consensus. Instead, they'd chosen control, and control breeds suspicion. People started wondering what there was to hide. While we obsess over 3i Atlas and parse NASA's questionable briefing, something bigger is happening in physics itself. The universe is revealing cracks in our understanding, not through alien visitors necessarily, but through the fabric of reality behaving in ways we never predicted. Throughout 2025, cosmologists and dark matter researchers have been quietly publishing results that don't fit the standard model, anomalies in how gravity works at certain scales, irregularities in matter distribution that shouldn't exist if our equations are correct. These discoveries matter because they change the context for everything we observe. If the universe is weirder than we thought, if physics allows possibilities we haven't imagined, then maybe objects like 3i Atlas aren't just anomalies in astronomy, but symptoms of a larger problem with our assumptions about how nature works. The dark matter mapping projects reached a milestone this year, with unprecedented resolution surveys of galactic halos and cosmic web structures. Multiple independent teams using different methods, gravitational lensing, rotation curve analysis, cosmic microwave background correlations, found the same troubling pattern. The distribution of dark matter at small scales, structures below the size of galaxy clusters, doesn't match simulations. Models predict smooth halos with predictable density profiles. Observations show clumpiness, substructure, unexpected voids, and concentrations that computer simulations can't reproduce without adding new physics. One research group described it as finding turbulence where we expected laminar flow. Another called it evidence that dark matter might interact with itself or with normal matter through forces we haven't discovered yet. The implications ripple outward. If dark matter behaves differently than we thought, then every calculation involving gravity at cosmic scales needs revision. That includes predictions about how objects move through space, how interstellar visitors accelerate or decelerate, what trajectories are possible under what we assumed were known laws. Some physicists started asking uncomfortable questions about whether these dark matter anomalies could affect interstellar objects directly. Standard astrophysics treats dark matter as essentially invisible, interacting only through gravity, irrelevant to small-scale dynamics like comet trajectories. But what if that's wrong? What if dark matter exerts pressure or drag at certain velocities? What if objects moving through interstellar space at hundreds of thousands of kilometers per hour experience forces from dark matter that we've never measured because nothing we've built moves fast enough to detect them? These ideas remain speculative, not accepted by mainstream cosmology, but they're being discussed seriously in theoretical physics circles, and they open disturbing possibilities. Maybe some of 3i Atlas's unexplained velocity residuals, the accelerations that don't quite fit standard outgassing models, aren't about outgassing at all. Maybe they're evidence of interaction with a dark matter component we don't understand, physics that becomes relevant only at extreme speeds in interstellar environments. NASA wouldn't mention this possibility because it's unproven, but it's also exactly the kind of alternative explanation that should be considered when conventional models struggle to fit data. There's another frontier where physics is revealing strange behavior: quantum effects at mesoscopic scales, systems too large for pure quantum mechanics, but too small for purely classical treatment. Recent experiments with macroscopic quantum coherence, maintaining quantum states in increasingly large objects, have pushed boundaries further than anyone expected. We're finding that quantum weirdness doesn't simply vanish at human scales, but fades gradually, creating a gray zone where objects can exhibit both classical and quantum properties simultaneously. Some theorists speculate that interstellar objects, spending eons in the near absolute zero temperatures of deep space, might preserve quantum coherence across surprisingly large structures. If that's true, their behavior near stars, as they warm up and decohere, could involve phase transitions and energy releases that look thermal but have quantum origins. It's another framework for understanding anomalous observations without invoking engineering or intelligence. Physics behaving strangely because we've never observed objects in these specific conditions before. But notice how these discussions happen openly in the physics community. Papers get published. Data gets shared. Anomalies are acknowledged and debated. Nobody pretends everything fits perfectly. Compare that transparency to NASA's approach with 3i Atlas. In cosmology, when observations don't match theory, researchers publish the discrepancy and invite scrutiny. Dark matter anomalies get announced in press releases with titles like, "Our models might be wrong, come help us figure this out." But with 3i Atlas, the agency presented a closed narrative, a finished story with no invitation for independent verification. Why the difference? Both involve fundamental questions about how the universe works. Both have implications for our understanding of physics. The only distinction is institutional ownership. NASA owns the spacecraft, the observation time, the data pipeline. They control access. And when you control access, you control narrative, which is the opposite of how science is supposed to function. If physics allows strange things, if the universe surprises us regularly with behavior that challenges theory, why are we so eager to declare 3i Atlas just a comet when the data quality is poor and the explanations require special pleading? The broader pattern here reveals something uncomfortable about how humanity handles anomalies, depending on where they appear. Anomalies in cosmology, in laboratory physics, in controlled experiments. These get celebrated as opportunities for discovery. Anomalies in objects visiting our solar system get suppressed, explained away, treated as threats to institutional credibility rather than invitations to deeper investigation. Maybe this reflects reasonable caution. Extraordinary claims about visitors from other civilizations do require extraordinary evidence, and managing public expectations around such claims is legitimate. But there's a line between caution and denial, between healthy skepticism and dogmatic rejection. When you find yourself needing increasingly contrived explanations to defend the conventional interpretation, when the footnotes contradict the headlines, when independent researchers using standard methods reach different conclusions than official agencies, you've crossed that line. You're no longer following evidence wherever it leads. You're defending a conclusion you reached before the evidence was complete. This isn't just about 3i Atlas. It's about how we approach the unknown more broadly. Throughout history, paradigm shifts in science were resisted not because evidence was lacking, but because institutions and individual scientists had invested too much credibility in old frameworks. Continental drift was obvious from maps, but took decades to accept because geologists had built careers on static continents. Heliocentrism was observable, but fought because it challenged religious and philosophical assumptions. Quantum mechanics was mathematically necessary, but philosophically uncomfortable, resisted by even brilliant physicists who preferred the certainty of classical physics. Every time, the same pattern. Anomalies accumulate, conventional explanations become strained. Someone proposes a radical alternative, institutions resist, eventually, weight of evidence becomes undeniable, and the paradigm shifts. We're taught this history as triumph of science over dogma, but we never seem to learn the lesson when we're in the middle of it. Right now, with 3i Atlas, we might be watching that pattern repeat. Anomalies accumulating, conventional explanations strained, institutions resisting, the difference being we don't yet know what the new paradigm will be. Maybe it's still a comet, just a really weird one that pushes boundaries of what comets can be. Or maybe it's something else, something that will require rethinking assumptions we thought were settled. Either way, the resistance to honest investigation feels familiar. And history suggests that when institutions fight transparency this hard, they're usually on the wrong side of the paradigm shift, defending yesterday's certainties against tomorrow's revelations. If 3i Atlas is a test of humanity's readiness to recognize something genuinely strange, we're failing spectacularly. But failures teach lessons if you're willing to learn them, and one lesson emerging from this mess is clear. We need better systems for detecting, tracking, and analyzing anomalous objects before institutional inertia and political calculation corrupt the scientific response. The technology exists. What's missing is will, vision, and infrastructure designed explicitly for rapid response to the unexpected. Throughout 2025, Artificial intelligence systems have reached capabilities that would have seemed impossible just years ago. They autonomously direct telescopes, analyze petabytes of data, identify anomalies, decide follow-up strategies, and execute observations without waiting for human committees to convene. These systems operate at speeds that bypass bureaucratic delays, making decisions in milliseconds based on probabilistic assessments of what's interesting and what needs immediate attention. If we'd had such systems fully deployed and trusted before 3i Atlas arrived, the story might have unfolded very differently. The current astronomy infrastructure operates on human timescales. Observation proposals go through peer review committees that meet quarterly. Telescope time gets allocated months in advance based on predicted scientific value. Data processing follows standard pipelines with built-in delays for quality checks. This works fine for stable, predictable targets like distant galaxies or known asteroids. It fails catastrophically for transient anomalies that appear without warning and disappear before bureaucracy can respond. 3i Atlas spent weeks passing through our solar system, closest approach to Mars, closest approach to Earth, multiple optimal observation windows. By the time NASA organized their response and released findings, the object was already receding. Opportunities lost forever. An AI-driven network wouldn't make that mistake. Sensors would trigger automatically. Telescopes would reorient within minutes. Data would stream to analysis systems that flag anomalies immediately, not after humans manually review frames weeks later. Raw data would post to public repositories in real time, making independent verification possible from day one. The bottleneck isn't technology, it's trust. Institutions don't want to cede control to automated systems that might surface politically inconvenient findings before messaging can be managed. Several research groups are now proposing dedicated rapid response missions for interstellar visitors, spacecraft that remain dormant in parking orbits until something interesting enters the solar system, then activate and pursue. The concept isn't new. Ideas for fast intercept probes have circulated for years, but 3i Atlas added urgency. One proposal involves a constellation of small spacecraft positioned throughout the inner solar system, each equipped with modest propulsion and instrument packages, networked to coordinate observations and relay data. When an interstellar object appears, the nearest spacecraft calculate intercept trajectories, some matching velocity for close-up imaging, others positioning for parallax measurements, all transmitting continuously to eliminate single points of failure or control. Another proposal imagines laser sail technology, using ground-based lasers to accelerate lightweight probes to extreme velocities, reaching interstellar visitors quickly enough to conduct flybys while they're still accessible. These missions would cost billions, requiring political support that doesn't currently exist. But the alternative is continuing to scramble reactively every time something unexpected arrives, handicapped by slow institutions and infrastructure designed for a universe that behaves predictably. What makes these future scenarios particularly fascinating is the possibility that we're not the only ones thinking about detection and observation systems. If 3i Atlas were engineered, if it were a probe from somewhere else, its designers presumably anticipated being observed. They would have known that any technological civilization monitors its local space environment, that unusual visitors attract attention. Maybe they designed the object specifically to appear comet-like under casual observation, but reveal structure to those looking carefully, a filter separating civilizations capable of detailed analysis from those who only glance. Maybe the entire mission profile was calculated to test whether we'd recognize signal beneath noise, whether we'd pursue anomalies, or accept convenient explanations. If that sounds paranoid, consider how we've designed our own interstellar probes. Voyager spacecraft carry golden records encoded with information about humanity. But that information is encrypted in a sense, requiring technological sophistication to decode. We assumed any civilization capable of finding the probes would also be capable of understanding the records. That's anthropocentric thinking. What if their assumptions are different? What if 3i Atlas carries information we're missing because we declared it a comet and stopped looking? There's an even stranger possibility that some researchers whisper about but rarely write down. What if future visitors, whether from 3i Atlas's creators or others, aren't biological at all, but entirely artificial intelligences embedded in spacecraft designed to operate autonomously for millions of years. Biological explorers face severe constraints: life support, limited operational duration, psychological effects of isolation, communication delays across interstellar distances. Machine explorers face none of these. An AI-driven probe could travel for eons, hibernate during transit, activate when entering a star system, conduct observations, decide autonomously whether to make contact or remain covert. It could mimic natural objects deliberately, using outgassing for propulsion while appearing cometary, maintaining radio silence unless it judges contact appropriate. From this perspective, every anomaly in 3I Atlas's behavior, the geometric structures, the unexplained accelerations, the apparent intelligence in choosing trajectories that maximize solar system observation while minimizing exposure to detailed scrutiny, all become consistent with a design mission optimized by machine intelligence operating on logic completely foreign to human thinking. We're used to imagining alien contact as first contact with alien minds. What if it's first contact with alien algorithms, and we never recognize it because we keep looking for biological signatures and missing computational ones? This brings us back to the core tension running through the entire 3I Atlas story. Is this a failure of transparency, NASA managing narrative rather than pursuing truth? Or is it something more fundamental, a failure of imagination, our inability to recognize possibilities outside conventional frameworks? Maybe both. Institutions structured around hierarchies and control will always prioritize message management over radical openness, especially when anomalies threaten comfortable assumptions. But individuals can choose differently. Scientists can refuse to accept convenient explanations when data demands better ones. Engineers can build systems that bypass institutional gatekeeping. Citizens can demand transparency and hold agencies accountable when they refuse it. The question isn't whether 3I Atlas was a comet or something else. The question is whether we're capable of handling ambiguity honestly, admitting ignorance when appropriate, investigating anomalies thoroughly before declaring cases closed. Because if we can't do that with one interstellar visitor, when we had months of warning and observation time, what happens when something arrives that moves faster, stays briefer, or reveals itself only to those prepared to see? The universe is not obligated to make sense to us. Physics doesn't care about our theories. Reality will do whatever it does, regardless of whether our equations describe it accurately. For centuries, science advanced through this simple discipline: observe carefully, model honestly, test rigorously, revise when evidence demands it. Somewhere along the way, institutions forgot that last part. They became invested in defending existing models even when observations didn't quite fit, explaining away anomalies rather than investigating them, prioritizing consistency over truth. 3I Atlas might be exactly what NASA claims: a natural comet with some unusual properties that will eventually fit conventional physics once we understand them better. Or it might be something we haven't imagined yet, not alien necessarily, but revealing physics we haven't discovered, or possibilities we haven't considered. Either way, the response we've witnessed, the controlled briefings, the poor image quality, the refusal to release raw data, the dismissal of independent analysis, this is not how science handles potentially paradigm-shifting discoveries. This is how politics handles inconvenient questions. And if we let political calculation replace scientific investigation, if we accept managed narratives over messy truth, then we've already lost something more important than any answer about one object passing through our solar system. We've lost the capacity for wonder, the courage to confront the unknown without flinching, the imagination to recognize that the universe might be stranger and more surprising than we ever dared believe. 3I Atlas came and went. Others will follow. The question is whether we'll be ready, not just with better telescopes and faster spacecraft, but with better institutions, better processes, and better minds capable of seeing what's actually there instead of what we expect to find. Because in the end, the most dangerous lie isn't what NASA might be hiding. It's the lie we tell ourselves, that we already understand the universe well enough to recognize what belongs and what doesn't, what's possible and what's forbidden. And that lie, more than any comet or probe or anomaly, is what keeps us trapped in a cosmos far smaller than the one we actually inhabit.